So I'm Wayne Zhao from Australian National University, and I'm very excited here to present our new garbage collector, LXR, which has a giant advantage over the prior work. So in general, in this talk, I'll discuss why low latency, high throughput GC is important, and why the design of production Java GC is intrinsically flawed, and I mean in a way that no engineering effort is able to fix. And I also show how our LXR's design addresses these fundamental issues. So first, imagine we have an interactive text search server. And the user keeps sending text search requests to the server, and the server keeps sending back responses, just like this. And imagine the server is returning Java, for example, Lucene. And what if a garbage collection happens when the server is still processing a request, where the user will get a delayed response with a higher latency? And you are not the only user. Typically, the server receives multiple requests from multiple sources at a time. So if the server is blocked by garbage collection, not only the running requests will be affected, but as new requests arrive, they will all be blocked and queued up, and the latency for all these requests will all increase. So this is mostly the main reason why most of the modern garbage collectors start to optimize for pause time. So let's do a quick overview here. First, G1 is the default garbage collector in OpenJDK, and it is designed to optimize for pause time. And it has 4 high-level key features: tracing, region-based, evacuation only, and stop-the-word evacuation. And for this stop-the-word region-based evacuation, G1 performs pauses and copies live objects in those fragmented regions and move them to the reserved empty regions. And after G1, the latest collectors further reduces pause time by performing more concurrent jobs. So C4, Shenandoah, and ZGC, although they are implemented differently, but they all share the common high-level key features. So they all perform tracing and are all region-based and all evacuation only. So if we pick Shenandoah and compare with G1, the only major difference is that Shenandoah performs concurrent evacuation, and instead of doing that in the pause. But unfortunately, for these modern low-pause collectors, their long-running concurrent GC threads will consume substantial processors. And this reduces server throughput, limits the rate it can process requests, and this will eventually lead to significant latency. So this shows that poor throughput will actually lead to poor latency. And this is also why our LXR optimizes for both throughput and latency. So this is the pause time curve for G1 and Shenandoah. We show the aerial search result because this is a widely used and also high demanding workload, and it has a very high allocation rate and imposes great burden to the garbage collectors. So in this graph, the x-axis is the percentile of the requests, and the y-axis is the pause time in milliseconds. And as you can see, Shenandoah has ultra low pause, much lower pause time than G1. And however, this is a latency graph, different to the previous pause time graph here, and also throughout the remainder of the talk, we will show latency that user actually experiences instead of simply the pause time. So, see the graph, it is super striking, right? So, although Shenandoah has ultra low pause time, it actually has much higher latency than G1. And for those concurrent copying collectors like Shenandoah, because they consume extra computation resource for concurrent collection. So the only thing you can do to improve its latency is to trade time for space. And here we show that if we assign Shenandoah with 10x more heap, it is now able to match G1's latency, but on a much smaller heap size. However, our objective to LXR is that we will have better latency than both G1 and Shenandoah, and also we will have competitive throughput than the two collectors. So, to achieve high throughput and low latency, we addressed 6 different challenges this year. And among all these challenges, it turns out that the first 2, immediacy and avoiding copying, they are really hard problems to solve. So let's dig in with these 2. The first problem is immediacy. So the tracing collector cannot reclaim objects timely. So for a traditional tracing collector to reclaim memory, it has to apply a transitive closure starting from the root pointers and recursively mark all the live objects in the heap. And so it has a few issues. The first, it cannot reclaim anything before everything has been traced. And also the parallelism of tracing itself highly depends on the shape of the heap. So this makes tracing intrinsically slow to reclaim. Well, however, LXR uses reference counting. Again, like the previous talk, to solve this issue. So the naive reference counting algorithm in 1960 simply checks this pointer update. Track each pointer update and apply a decrement to the overwritten object and an increment to the new object. And it also reclaims object with 0 reference counts. However, this has completely different issues. The first is cyclic garbage, and the second problem is the mutator overhead, because you have to apply 2 atomic operations for each pointer update. LXR solves the mutator overhead issue by introducing temporal coordinating step by step. The first step is the deferral RC in 1976. And we also adapt the coalescing RC by Levanoni and Petrenko in 2001. And actually, Petrenko probably sits over there. Yeah. And so this is actually a very interesting and also important optimization. So it observes that if a field is updated multiple times, all these intermediate pluses and minuses, they can actually all be cancelled out. So what RC really cares is the first overwritten object and the latest target object. And we also applied the implicitly dead optimization in 2012. So with these 3 as well as the other minor optimizations, we are now able to completely remove the mutator overhead problem and leaving the cyclic garbage being the only problem left. So with RC and its timely reclamation, this will bring us high performance. And the second problem is the dependence on copying. So most of the modern garbage collectors reclaim memory only by performing evacuation. So the first issue for this is that for coherency, if you move objects, you have to update all the pointers pointing to those objects. And also copying itself consumes large memory traffic. And for some garbage collectors, you have to have a large copy reserve to fit the worst case survival ratio. And these 3 reasons makes evacuation intrinsically expensive. And even worse, for a low-pos collector that also performs strictly evacuation, it has no choice but only performs concurrent copying. Because copying is expensive and you can't do all of such copying. Sorry? Yeah, you can't do all of such copying totally in the pos. Well, LXR solves this issue by using the Immix Heap with recycling and opportunistic copying. So the Immix Heap divides the heap into blocks, and blocks are further divided into smaller heaps, smaller lines. And as an example, so to evacuate fragmented objects in the evacuation set, Immix will apply a transitive closure starting from the root pointer, and so let's use the example here. Starting from the upper graph, it will follow the root pointer and copies the first object to a recycled line. And it will skip the next 2 objects because they are not in the evacuation set. And also the last object will also be evacuated to the recycled line. So with this recycling thing, it can recycle 3 lines for future allocation so that it don't need a large or even any copy reserve. And also with opportunistic copying, it is in such evacuation process, it's able to stop at any time as long as some time or space constraint is met, and it will simply leave everything else just in place. So this is how we perform judicious targeted and also minimal copying in the pos, so that we don't need to do any concurrent copying. Okay, now let's go through some other high-level design decisions of LXR. LXR is designed to achieve high throughput and low latency, and we've already showed that how immediacy and avoiding copying using Immix Heap helps with throughput. Now let's skip the next topic for a moment and discuss how short pauses, defragmentation, and concurrent marking helps with latency. So, for example, imagine we have a multi-threaded application running. A traditional stopped word collector would perform periodic and lengthy pauses, and it will interrupt the mutators and perform all the marking, evacuation, and the reclamation jobs totally in the pos. So this makes the pos generally large and expensive. On the other hand, the concurrent copying collectors tend to make the pos as short as possible. But actually, the amount of GC work is increased. It has to shift this GC work from the pods to these long-running concurrent GC threads. And so it is obvious here that these concurrent GC threads consumes extra computation resource and will eventually slow down the application. However, LXR chooses to perform regular brief and high effective pauses. Because we have opportunistic copying, so we can perform all our limited copying jobs totally in the pause. Well, this will make the pause time slightly larger than the concurrent copying collectors, but by doing so, LXR only needs to perform occasional concurrent marking, a part of the reference counting jobs, and the reclamation work in concurrent, so that it won't slow down the application so much. And LXR also performs incremental defragmentation. The problem for this is that moving objects actually requires a sort of global knowledge to track and update all the pointers pointing to these moved objects. But the problem is that reference counting is intrinsically a local operation. However, Sharia exploited that such complete knowledge can actually be achieved either when doing copying after the first RC after an object is born, or copying during a stop the word full heap trace. Well, the second one is no longer an option to us because we don't want to do the tracing in the pause, but we still adapt the first option. And we also have new observation that we can actually add remembered sets to RC. So this is actually the most important innovation for us to be able to move objects with reference counting. And in general, we group Immix blocks into contiguous regions, and by remembering those cross-region pointers, we are able to reclaim and evacuate regions without a full heap trace. And LXR also uses the concurrent marking to solve the cyclic garbage issue. We use snapshot at the beginning algorithm, and the intuition is that garbage is stable. So SATB will create a virtual snapshot of the heap at the start of the marking, and it will perform the marking on the snapshot. Because the mutator can also update the pointers, so before each pointer store, you have to capture and track each overwritten object properly. And the implementation is also simple. We adapt the observation from Masachi and Pentrick that SATB barrier can actually be folded into coalescing RC red barrier. And we also have to solve other complications such as RC can deleting objects during concurrent marking. Okay, so far we've gone through 5 of the high-level design decisions of LXR. Now let's discuss one more important low-level implementation detail. So for the implementation, LXR actually introduced plenty of innovations that could be discussed. We've already covered the first 2, but unfortunately the time only allows us to discuss one more. So the write barrier. In general, LXR builds coalescing RC, SATB, and remembered set maintenance using one low overhead and high precision write barrier. Let's take Java's put field instruction as an example. The instruction simply stores the value object to the location of the field. And our barrier only cares about the first modification of the field, and the slow pass pushes the overwritten object to a deck buffer, and the location of the field to a modified buffer. And it turns out this is everything we need to our implementation. For coalescing RC, we scan the fields in the modified buffer, load the target objects, and apply increments. And we also apply decrements to the objects in the deck buffer. And for concurrent marking, we simply mark and scan the objects in the deck buffer. And for remembered set maintenance, we scan the fields in the modified buffer, remember those pointing to the evacuation set. This is how we build 3 semantics using one low overhead write barrier, and the overhead is only 1.6%. Okay, so now let's see how LXR performs. So first, for the implementation, we did our implementation on OpenJDK 11, which was LTS at the time of our development. And we also used MTK for our implementation. And for the evaluation, we used a couple benchmark suite and comparing with 3 different production garbage collectors in OpenJDK. And we did our evaluation on multiple platforms. The results are similar. So here, in this talk, I'll only show the AMD Zen 3 results. And this is the same latency graph as shown before. And note that we do not report ZGC results because LU search is running with relatively small heap size and cannot run with ZGC on OpenJDK 11. And this is the result with LXR data. So as you can see, LXR has much better latency than both G1 and Shenandoah. And these are the other 3 latency-sensitive benchmarks in the couple suite. And these are all widely used applications and represent diverse types of the workloads. Same as error search, we do not report ZGC results to Tomcat because it also uses relatively small heap size. And so it is obvious here that LXR has much better latency than all the other collectors for most of the cases, especially for Cassandra and Tomcat. And we don't just care about latency. For the other benchmarks, we also report the throughput results. For Shenandoah and ZGC, because they do concurrent copying and introducing heavy read barriers, so they generally have much worse throughput than G1. But our LXR has slightly 4% better throughput than G1. And because garbage collection is fundamentally a time-space trade-off, so we also measure the sensitivity over different heap sizes, ranging from 1.3x of the minimum runnable heap to 6x. So for the latency, LXR is much better than all the other collectors for all the heap sizes. And for the throughput, LXR is also same or slightly better than the others. Okay, so the conclusion is that first, existing low-cost collectors do not yield low latency because the lack of immediacy, the dependence on copying, and the low throughput. And these are actually the fundamental issues to the algorithms of the collectors and cannot be fixed by simply putting extra engineering effort. And we also introduced LXR to focus on latency instead of the pause time. We perform judicious stop-the-word copying, as well as other key innovations such as RC remembered sets. And we also demonstrate the ability for LXR to achieve high throughput and low latency. Yeah, thank you for your attention.
In the talk you talked a bit about the sensitivity that these collectors have to the total heap size.
Yeah.
And oftentimes the performance seems to improve when you give it a bit more space. So I was wondering what's sort of the intrinsic problem with that? Like, why do we not just give the collector or give the program as much memory as we have?
Oh yeah. So that's because here, if we compare the graph, see the gray line is the Shenandoah with 10x more memory, and the orange line is the Shenandoah with like the same memory as G1. So yeah, you can achieve high latency with by simply assigning more memory, but that does not solve the issue. It's just hiding the issue. But
it looks like it solved the issue, though.
No, it's not solved the issue. The GC is a time-space trade-off. So by assigning more memory, you are just hiding the issue, but the issue still exists. And as I described before, the issue is mainly the dependence on copying and the immediacy.
Yeah, so you're saying if the program ended up using enough memory, then eventually you would hit the same blow-up at some point.
Yeah, but why not just use G1? You'll have the same latency, but using a smaller heap size.
Okay,
right?
Thank you.
All right, so while we're on this slide, a quick clarifying question about this. So there's also a dimension of oversaturation on the CPU side. So any server, if you fork, keep increasing the number of worker threads you're forking, eventually the server is going to behave badly, right? So these are using the same number of worker threads for the server in these three cases. And how many worker threads is that?
You mean the number of worker threads?
Yeah, so you got like a 40-core server or whatever it was, and...
Yeah, so we default... for our XR, for our implementation, I think for the stopped word collection, we use all the cores for the stopped word parallel GC, and for the concurrent collection, the concurrent marking, we use half of the threads.
Oh wait, sorry. In this graph, you're using n/2 mutator threads.
Oh no,
for platforms
in this graph, we just for the G1 Shenandoah and the Shenandoah 10x, we just use the default parameters in OpenDDK.
Okay, I'll ask you more about it offline. But the question I really wanted to ask was, what would you do differently? Oh, all right, sure thing.
Yeah,
we're behind time.
Discuss with you later. Yeah.